So, welcome to the final session of the Incorrectness workshop. Congratulations, you made it this far. Our next talk is by Zhou, and a great title, I love it, Type-Based Incorrectness Reasoning, or, this is the favorite part, well-typed programs must go wrong. Take it away.
Yeah. Okay. Hello, everyone. Welcome to my talk. Type-based incorrect reasoning, or we say the well-typed programs never go wrong. I'm Zhou, and this is joint work with Benjamin Delaware and my advisor, Suresh Jagannathan from Purdue University. So first I want to show you the big picture of the verification. In general, we have two frameworks to do verification, the program logic and types. So if we want to verify the safety property, we treat this logic or the types as an over-approximation of the programs. For example, in the program logic for the imperative language, we have whole logic. And in the world of types, in the functional language, we use the refinement types. But if we shift from the safety verification into the completeness verification, and we also go from the over-approximation to the under-approximation, so Peter here introduced the Incorrectness Logic, and recently we introduced the coverage type in the world of the functional language and types as an analog to do the under-approximation reasoning. So published in the PLDI last year. So let me tell you something about the coverage type. So the program we try to verify is actually the implementation of test input generator. Here is example. This is the NetGen. It's a natural number generator. It's implemented by the InGen integer generator by take its absolute value. And the property we want to verify is the coverage completeness. What we say the test generator must generate all test cases satisfy the given property. In the example above, we will require the NetGen must return all natural numbers non-deterministically. What happens if an implementation loses the coverage? So consider the following buggy program. It's a 10 divided x minus 10. X can be an arbitrary natural number that is the result of a natural number generator. And if we lose the coverage, it means that the test cases cannot cover a single case x equal to 11, x equal to 13, and that exactly the case can trigger the division by zero exception. So if you lose the coverage, it means that we can fail to find the bug regardless how many times we run the test, regardless how many test cases generated by the test generator. So the coverage completeness is quite important for the implementation of the test generators. And I will talk a little bit about this language we focus on the syntax semantics. So in general, it's a simple type lambda calculus, but with non-deterministic semantics. So a term here will reduce to multiple values instead of the single one. So the constants is a term, and 1 can reduce to a singleton value 1. And we also have non-deterministic choice, 1, O plus 2, can reduce to 1 and 2, non-deterministically. And the NetGen can reduce to all possible natural numbers, and the InGen can reduce to all possible integers. So what is the definition of the coverage type? So that's quite similar with the refinement type. Here is an example of the refinement type, which consists of 3 parts: self-reference, base type, and qualifier. So the example above, the base type is integer type, and the qualifier is v equal to 1 or v equal to 2. V here is a self-reference, indicates the term self. And if a term E can have a refinement type, it means that for any value E can reduce to, that value can satisfy the qualifier phi. On the other hand, the coverage type is quite similar. We use a different bracket, use a different colors, the color blue, to distinguish from the refinement type. And they have the same structure. The only difference is the interpretation of the qualifier different. So the meaning of the coverage type, if you look at it, you will find that the qualifier here is actually in the left-hand side of the implication instead of the right-hand side. So it means that any value satisfies the phi, the term must reduce to it. So the coverage, in some sense, implies the reachability. So I will give you several examples about the coverage type and refinement types. Here's the 4 refinement types and 4 coverage types. If we focus on the first term, the constant 1, then it can have all possible refinement type. Additionally, we'll have the coverage type v equal to 1, because the term 1 can reduce to a single term value 1 that covers the value v equal to 1. And for 1 O plus 2, it can have additionally besides can cover v equal to 1, but can also cover the v equal to 1 or v equal to 2. And for the NatGen, it can have 3 coverage types because it can cover more things. And for NatGen, it can actually have the top type. The top means that the NatGen can cover all possible natural numbers, integers. So the next interesting thing is subtyping. If we try to see the inclusion relation of these qualifiers, and we try to take a look at the subtyping between these coverage types, and you'll find they are contravariant. So look at the v equal to 1, and v equal to 1 or v equal to 2. That is 1 is included by that, and v greater than 0 in the top. And you see that is a contravariant. That is different from the standard refinement type system, which is a covariant from this inclusion relation between these qualifiers. So in some sense, we say the coverage type inverts the standard subtyping relation. And there's a very similar things happens in the Incorrectness Logic paper about the symmetry rules, and it also inverts the standard Hoare logic. So after introduces the coverage type, and we compare the coverage and incorrectness verification. So when we try to do the incorrectness verification, try to prove a program is indeed buggy, it's actually try to prove a reachability. So we say the program must reach some state, satisfy the given property. Here's an example from the original Incorrectness Logic paper. We say if we assume the x z equal to 11, and we execute this program, and we want to say there's a program state z equal to 42 is reachable. And our coverage type try to verify the coverage completeness. It means that test generator must generate all test cases, satisfy the given property. As we said before, the coverage can imply the reachability. So that is a very natural question we want to ask. Can we use coverage type to verify the incorrectness of the property of the program? The answer is yes, and that is the main topic of this talk. So the type-based incorrectness verification. And in the following slides, I will tell you how to do it, and that is quite simple. By just rewrite the program a little bit, and the coverage type can already handle it. So let's get started from the same example we showed that before. And the intuition of the type-based incorrectness verification is try to simulate the test procedure. So what it means about test procedure? So the first step, we try to rewrite this program from the imperative language to the functional language, because currently coverage type is designed for the functional language. So we say when the x is even and y is odd, we return 42. Otherwise, we directly return z. So that have the same meaning from the program on the left-hand side. And the second step is quite interesting. We add a random initialization procedure. That is consistent of the precondition z equal to 11. We say z equal to 11, and the x and y have no constraint. They can be arbitrary integer. So we simply say x and y are a result of some int gen. So in some sense, you can treat the random initialization procedure, generate different test cases non-deterministically, and we test the original program. So that's how I say I simulate the test procedure. So in another perspective, if you compose these two parts together, and itself can be a large test generator. In that sense, we can also do the coverage type check. So what we do here is that we rewrite the post condition into the coverage type, because here we don't care about it's a functional language, we don't care about the x and y. So the qualifier of the coverage type can only simply say the v equal to 42. That is the thing we're interested in. And if the coverage type check success, it means that the whole test generator can cover the value 42. In other way, we say the coverage can implies irreachability. It means that the program in left-hand side indeed reach the z equal to 42. So that is how we do the type-based incorrect verification by the coverage type. the original Incorrectness Logic paper additionally can track the correct and erroneous execution by the label OK and error. How can we do that in our coverage type? So take a look at another example. It's also from the original Incorrectness Logic paper. And what we try to solve this problem, just use a product type to check both correct and erroneous execution. So like before, we also rewrite this program into the functional language, and we add a random initialization procedure. And additionally, we define the type of status can be OK or error. And that works like a error monad, which is a function for full return not only an integer, but a product with status is indicate if that execution is OK or error. So if x is an even, it's just error. Otherwise, that will be non-deterministically return OK or error. So we also rewrite the post condition into a coverage type. So this label error or OK is directly rewriting into the part in our qualifier st, which means the status is equal to error or OK. So that is how we track the correct and erroneous execution like Incorrectness Logic in coverage type. And the last part of things about the function type. Of course, this type we show here is the result type of the full. But what's the function type? Function type also has the parameter type. So what is the type of the parameters? Actually, there's two choices. The parameter can be over-approximated, can also be under-approximated. So what is here's example of the over-approximated type. And the meaning of this type means that all values satisfy the property phi2 that is in your result type must be returned by the function call for each input value satisfies the property phi1. Here is the for each. And if you use this under approximation parameter type, it's similar like the left-hand side, but we use different brackets to indicate that it's under approximation parameter. And the meaning of that, the two lines, the first two lines are the same. The difference that we say is for some input value satisfies the property phi1. So the difference that one is for all, another exists. So in some sense, because the left-hand side is for all, the right-hand side exists, the over-approximation parameter type is also a subtype of it's more precise than the under-approximation type. But another direction doesn't hold. Actually, we need to make a trade-off between the precision of the specification. It's not to say we should always use over-approximation parameter types, or we should also use under-approximation parameter type. Here's an example. Consider the following program. We say the x can be arbitrary value, and we take the absolute value of the 10 to divide x minus absolute value of 13. And of course, when x is equal to 13, there's a division by 0 exception. So this program is buggy. And that is something we want to prove. The program is indeed buggy. So this incorrectness property can easily translate to the following coverage type. The parameter type is under-approximated. This means that it can be there exists some integer. So that is the top type. And the post condition says that is error. However, what is the type of the ABS? The ABS, if we take still treat as under approximation type, maybe we can say that v equal to 10 is a parameter type. It works for the first application, but fail for the second because the 13 cannot cover the value 10. And we say if the v equal to 13, it fail in the first case. If we disjunct them together, they fail in both cases because the 10 cannot cover both 10 and 13. And if we conjunct of them, so that is simply a button type, itself is wrong. So actually, we don't want the under approximation type here. We want the over approximation type. It's actually very precisely describe what happens if you feed me a 10, I return you 10. If you feed me a 13, and return 13. So in that sense, both under approximation type and over approximation type we needed. So our future work to try to get the benefit of both of them. Okay, so here's the summary. If people want to do the type-based correctness verification, we can use this refinement types, where we treat the types of over approximation of the program, and we can say well-type program never go wrong. On the other hand, if we do the type-based incorrectness verification, we can use a coverage type, and we treat the type as the underapproximation. And we can say the well-type program must go wrong. So maybe we can design the type system to unify both of them. We can both over-approximation and under-approximation. That is a thing we'll try to explore. Okay, thank you.
Thank you so much. Questions for Zhou? I think Stephen.
You never show an example with a loop or recursion. Is it because you have a problem for under-approximation and proof terminations, or you don't like iterations?
Yeah, so if I understand correctly, you asked me that I don't show any example about loop or recursion. And
Why?
if that's a problem, no. I mean, in order to prove this coverage or the reachability, all this loop must be terminated. So my type system will do the check to guarantee all this loop will be terminated, just like how we do that in Cog. We have some well-founded relation on the loops or recursion.
Okay, so you have a method to prove termination.
Yeah.
Okay, great. And you can explain this method?
Can you repeat that?
Which method do you use to, that is, you say I have a well-founded order, okay?
Yeah.
How do you find it?
Oh, so our type system requires this we have some universal built-in well-founded relation for this basic type, and the data types is a structural decreasing order.
So you have predefined
Yeah,
order that you try, and if you are not in that case, what do you do?
Yes, like all possible verification tools. If I cannot prove it, it can see nothing.
It's not typeable, okay.
Yeah.
Thanks for the talk. So I don't quite understand the tagline, well-typed programs must go wrong. But is it not the case that you can type an expression with a function type, but it doesn't necessarily go wrong?
The way you say, if I understand it correctly, you say you don't, you have, your question answers my statement, well-typed program must go wrong, especially for the functions, right?
That's right, yeah.
So what do we mean we go wrong is that in some sense the function itself never go wrong. It's go wrong when the function application in some case. And in order to say that in the future the function go wrong, we actually say that some reachability property for this function. In that sense, if it proves the bad reachability property for this function implementation, we say the function is somehow go wrong in the future. I don't know if that satisfies this answer.
Yeah, that makes sense.
Okay.
Thanks.
Any other questions for Zhou? Okay, let's thank him again.
Okay, thank you.